Hey class, Adam Ward here. I want to talk to you today in the first of a series of two videos here about activated sludge treatment. In this video, we're going to focus on microbial growth. Alright, so just to remind you, we're looking at a typical wastewater treatment process in the US, and we're focused today in this aeration basin, which is the first step of secondary treatment. And again, this is where we're taking the organic material that we've been talking about as biological oxygen demand, or BOD, and basically converting that into microbial biomass before we settle it out in the secondary clarifier. Okay, so there are two key reactions that are happening here. The first is microbial respiration. So the organic material that we have supplied to the wastewater treatment plant, we are providing oxygen, and we're allowing microbes to use that as part of their respiration. So they're gaining energy by decomposing. And the second form is actually the creation of new cellular material, or the growth of new biomass, in which our organics are taking up oxygen, nitrogen, and phosphorus, and producing new cellular material, which we can later starve in the clarifier and get to settle out. So in that right-hand side of the second equation is just a typical ratio for microorganisms. Our organic material will get into the secondary clarifier, and then that will become what we've been referring to as sludge. A small amount of that will get recycled back around the system to basically seed the next population, but a majority of that will be what's called wasted, and we'll do something else as indicated with that anaerobic digester down in the bottom. So within our within our aeration basin, we're generating a fairly complicated food web. We're supplying particulate organic matter and dissolved organic matter, indicated by the boxes in white. And the arrows here are trying to express the dominant consumers of those in the higher order or higher level organisms that exist and feed upon those. Now, one thing you'll notice here in comparison to a food web you might think of drawing for an ecosystem, there is no primary production here. The key energy source is supplied in the waste that we're putting into the system. The combination of this microbial biomass along with the water that it's moving with is what's called mixed liquor suspended solids, or MLSS is the common abbreviation for that. And the other one that we'll use occasionally is mixed liquor volatile suspended solids. And the difference being that V for volatile, these are the suspended solids that are thought of as organic, and we measure that by burning those off at 500 degrees centigrade. So often people will prefer to use MLVSS because it is more representative of the amount of biomass that is organic. So any inorganic or non-reactive solids would be excluded because those wouldn't be burned at 500 degrees C. They would remain. So you think they're like some carbonate mineral, for example, that made it through our grit chamber and our primary treatment step. So in thinking about microbes, we're going to take an approach that looks like what's called logistic growth. So first I want to contrast this to something that we're more comfortable with, having dealt with earlier in the semester. So if we think about the number of organisms through time, if we represent this as exponential growth, as indicated in red, what we're saying is that the number of organisms, that the change in number per change in time, dn dt, is equal to some growth rate, mu, multiplied by the number n. And of course we can separate variables and integrate and get an expression that describes the population as a function of mu, which again is that growth rate for the organism. Now, this is seldom the case when we are in a real system because exponential growth indicates that there are no bounds. Much more common is to represent this as a bounded form of growth, or a logistic growth in this case. And what happens here is early on we may see exponential growth, but populations level out at a carrying capacity. Now, why might this happen? Well, broadly, there's a few reasons, but they primarily boil down to limitation of resources, whether that's space to survive, whether that is a food resource that's in high demand, or disease that's associated with overcrowding of a population. So rather than represent microbial growth as unlimited, we typically will represent it with this logistic growth type model. And the key thing that's added here is this last term. So it looks just like exponential, but then we add this term that basically throttles back growth relative to some carrying capacity, represented by that capital K. So the job of that 1 minus n over k is to basically slow down the growth as n approaches k. So as that population approaches the carrying capacity, we basically throttle down that growth rate, so it causes it to level off. So Monod was a French scientist, and in 1949 described microbial growth using this approach. He said, no, microbial growth is not unlimited. Microbial growth is a function of which microorganism we're looking at and the key limits on its ability to reproduce. And so sort of the manifestation of that mathematically is written here in black now. dx dt, where x is the population, or where we had previously used number, we're describing now the concentration of microorganisms, so the number per unit volume. It's related to, on the right-hand side, the maximum growth rate for that microorganism, so mu max, multiplied by x, that concentration, multiplied by s, the concentration of a limiting resource. And that s is used here for substrate. And so your textbook uses an S as well. You can think of that as the limiting food source. And in our case, we're thinking about that as biological oxygen demand, which of course is the organic material that we're supplying. Throttling this down is this idea of a half saturation constant. And so that's asking, what amount of substrate do you have when you reach half of the growth rate? So Ks is calculated as basically the concentration, again, concentration of substrate when you reach half of your maximum growth rate. So what's written there in black describes the growth part of microbes, and of course things that grow and live will ultimately die, and we'll represent that death as a first order coefficient, so a minus kd, think of d as decay or death, times the concentration. And this is called an endogenous decay rate, but for our purposes we can think of it as a death rate. And so what is the net growth of microbes? Well, we can put those two together. It's the growth in black minus the death shown in orange. And so this would be the application of Monod kinetics to describe microbial population growth and death. Now, in the same way that we're interested in describing the population of microbes, we've already sort of implied that there's this coupling to how much substrate is present. Both of those, the microbial term on the previous page in black has this value of S in it for substrate. But of course, as microbes grow and use substrate, we expect the amount of substrate to change. And so in order to model substrate, we need a way to link these together. So we need to link together how much biomass gets produced as substrate gets consumed. And the way we do that is with what's called yield, and that's a capital Y for its representation. What you can really think of yield as doing is basically serving as a conversion to say, how much biomass do you grow per unit substrate consumed? So yield is this critical translator, if you will, between the substrate equations and the biomass equations, or between x's and s's in this particular problem. And so from that definition of yield, we can directly relate substrate concentrations ds dt to biomass concentrations dx dt. Now you'll notice that there's a minus sign that showed up. Why? because when biomass goes up, substrate goes down. We need to create that inverse relationship. So the addition of X needs to cause the depletion of S. And we already had an equation for dx dt on the previous slide, so we can go ahead and plug that in and get this new equation written in blue. And you'll notice there's no minus kd term in there. And that's not a typo. That death term is independent of substrate, right? The actual dying or decay or removal of a microbe doesn't consume any substrate. So substrate is only consumed when it's growing and feeding and using that organic material as its source. All right, so that's the basics on how we represent microbial growth. And next lecture, you will see me talking about how to do this within an aeration basin and actually design one of these. Thanks all, and I appreciate you paying attention.